Hey everybody, welcome back to my YouTube channel. In this video I want to give you some insights on how I refined a process that allows you to create your own PCB prototypes at home. This method of creating PCBs has existed for a few months now on YouTube. I first saw this process in this video right here. It inspired me to try it myself and improve this method a little bit, since in the video only a one-layer PCB with through-hole parts is created. I, however, wanted SMD parts and a two-layer board. In the first part of this video, I will explain the process quickly, and then in the second part, I will give you a step-by-step tutorial for it. There is also a GitHub repository with some example projects, a short summary document, and useful Python automation scripts for Kicad. I put a link to that in the description. Now, what do I mean by high quality? Well, I have some examples right here for you. Those PCBs have all been created by me at home. Really, the most important factor of quality with PCBs is their precision. In other videos on YouTube that show DIY PCBs, you always see PCBs with big through-hole components. But as you can see here, I am using SMD parts with pitches as small as just 0.5 mm in a QFN package. As a quick reminder, the pitch refers to the distance between the center points of two neighboring pads or pins. Most through-hole components have a 2.54 mm pitch, which is much larger and therefore easier to work with than the parts I am working with. So how do I achieve this high precision? I will explain to you by giving you a summary of the process first. We start out with a one-layer copper board. The base is FR4 and the copper layer is 35 micrometers thick. The thickness is 0.8 mm in total. We now use spray paint to cover the entire copper side of the board with black paint. When you do this, make sure to apply the color evenly by moving across the board. The paint needs to be water resistant. After the paint has dried, I use tin snips to cut the copper board into smaller pieces. I now stick double-sided tape to the backside of one of the pieces. After that, I use this tape to stick the copper board into the laser engraver's working area. After that, I reference the laser position and I manually adjust the focus of the laser. Now it is time to use the laser to remove paint from the board in all of the spots where we want the copper removed later on our PCB. This takes a couple minutes depending on the size of your board. This process will work with any diode laser engraver with a wavelength of 455 nanometer. This means you don't have to spend thousands of dollars for fiber lasers or similar expensive devices. Diode lasers are the most affordable type of laser engravers, with some starting below $200. After the laser is done, it will look like this. There's still a lot of burnt paint dust on the board, but you can already see the PCB pattern. Next, I rinse the leftover paint dust off with water. I make sure to rub my finger over the board in all of the exposed spots to remove the dust completely. It is important to do this to not contaminate the etchant solution. The PCB will now get immersed in a container with distilled water mixed with sodium persulfate as our etchant solution. This liquid will remove the copper at the temperature of 45 degrees Celsius. It takes around 10 to 20 minutes to remove all of the copper. Creating bubbles in the water helps speeding up the etching process. It is important to monitor this process closely to remove the PCB from the etchant at the exact right time. Leaving the PCB in the etchant too long will cause under-etching. Taking it out too soon will cause the board to have short circuits. The PCB now looks like this. The etching process is done. Now we need to remove the paint as it is no longer needed on the board. For this I use acetone and some kitchen tissues. As you can see, I created the backside of the PCB on the same board as the front. I will cut both sides out with the tin snips again. The backside was printed mirrored. It can now be stacked onto the front side board. Together they have a thickness of 1.6 millimeters. The boards are still not connected firmly together. We now drill all of the through holes in the board. For drilling the holes, I use a high-speed rotary tool at 25,000 RPM with a small drill bit. I recommend getting a drill press attachment to drill in a perfect 90-degree angle, as well as a vacuum cleaner to suck up the PCB material. With the holes drilled, we can now use rivets to connect both sides of the PCB together and, most importantly, create true hole connections between both sides of the PCB. To firmly press the rivets into the holes, I use a rivet press device. The last part of the process is the same as for every other PCB. All of the parts need to be soldered onto the board. I recommend starting with the SMD parts and then continuing with the through hole parts. At the end, we have a beautiful working PCB that we can now use for our project. This board here is an adjustable overload protection circuit that I came up with but haven't validated yet. I can now check if it works as intended in the next couple of days. After this short summary, let's quickly talk about the motivation behind this process and compare it to other methods of electronics prototyping. The most beginner-friendly way of prototyping electronics is using a breadboard like this. You don't have to solder, big circuits can be created very quickly, but if you want to experiment with more exotic components, or you need either high voltage, high current, or high frequency signals somewhere, this is not an option. Currents higher than 1 amp are not recommended, mains voltage is an absolute no-go, and high frequency circuits won't work as intended. I have a very good example for that in this photo right here. You can see a 8 MHz square wave signal coming from an ESP32, which is completely messed up due to the bad wiring. The wiring I'm talking about goes through a breadboard into a camera module and looks like this. Another well-known method of electronics prototyping is using perf board like this. Because like breadboards, this method is so straightforward, I won't go into detail explaining it. Basically, you just stick your through hole components into the board and you solder them together with solder traces and wires like this. This method is supporting higher currents. You can create very thick solder traces and have multiple amps with no problems. Using high voltages on perf board is still not recommended, as the not used holes in the board can cause arcs. I personally would not trust a mains voltage circuit on a perf board. The holes in the board can also create issues with high frequency signals by creating unwanted capacitance between connections. I also wouldn't recommend going anywhere higher than a couple of megahertz on a perf board. There's also one other method worth mentioning when it comes to prototyping, and this is what I call air wiring. It looks like this. Because I consider this method so difficult and time-consuming, I would not recommend anyone to try it, but I have to admit that if it's done right, it looks very cool. Before I start with the full tutorial, let's talk about who this process is aimed at. Let's just get one thing out of the way: do not use this process in a production. Even at small scale, it is just way too time-consuming. If you need more than 10 copies of your board, I recommend ordering a PCB from a professional manufacturer instead. The process is ideal, however, for small-scale prototyping. You can use around 90% of all available parts at the moment, excluding SMD parts with a pitch lower than 0.5 mm and BGA packages. Pretty much every other part type is supported. Also, if you want to go with high currents, high voltage circuits, or high frequency signals, if you use the correct design guidelines, you can do everything you could also do on a professionally manufactured PCB. To summarize, this is the perfect prototyping method if you want to design professional electronic devices, not just, let's say, a basic Arduino LED blinking circuit. I think this process can fit very well into a lot of research and development departments or university labs, for example. It allows for elegant, high-quality prototypes that are cheap and quick to manufacture. You can turn a board layout in Kicad into a finished PCB within an afternoon at negligible costs, requiring a decent bit of manual labor, however. I created this comparison chart here to give you an overview of the different prototyping methods: air wiring, perf board circuits, breadboarding, and homemade PCBs. As you can see, homemade PCBs perform the best with high current, high voltage, and high frequency, as well as SMD parts, while still being decently quick to set up and modify. Performance with high voltage, high current, and high frequency is of course depending on the quality of your board layout. Now let's get started with the tutorial part of this video. I will first cover the shopping list. The initial investment will be somewhere between $1,000 and $2,000 depending on how much equipment you already have available. Of course you will need a laser engraver. It should be a diode laser with a wavelength of 455 nanometers. I recommend a model with at least 10 watts. The focal spot size is also important. It should be as small as possible. You will also need to buy a version of the software Lightburn to control the laser. I also have a housing for the laser. This one includes a fan that can connect to an air tube and a light source in the housing. Both features are highly recommended. Also, you will need a honeycomb work plate to put it under the laser. For safety reason, you should always have a fire extinguisher nearby. You will also need some goggles which block out laser light. Make sure they are certified for 455 nanometer wavelength. Furthermore, I recommend some regular safety goggles, a proper breathing mask, a vacuum cleaner for dust extraction while drilling holes in the PCB, and a camera so you can monitor your laser engraver without having to be in the same room. You will also need an etching setup like this that includes an air pump and a heater, also a chemical resistant surface to put it on top of. Also you will need a funnel to transfer liquids, distilled water, sodium persulfate as a powder, and a container for the etchant. Also you should get yourself some rubber gloves, normal gloves, and some tissues for cleanup. To make the PCBs, you definitely need some FR4 base material with the thickness of 0.8 mm and 35 micrometers of copper on one side, some acetone, isopropyl alcohol for cleanup, black spray paint, a metal container for the acetone, and a multimeter for quality control. To make sure you don't mess up your gloves, you should get yourself a lab coat. Also, you need a high RPM rotary tool, a drill press attachment for it, some tin snips, and a magnifying glass. At last, you will need drill bits. I recommend getting a set, some tweezers, PCB rivets, and some double-sided tape. You will also need the rivet press in this picture and a tool set for each rivet size that you are using. You will need to get drill bits which are the same size as the rivet's thickness. To assemble your finished PCBs, I recommend the following equipment to work with the small SMD parts: a hand soldering station, a hot air soldering station, flux, solder paste, a fume extractor, a good light source, solder tin and solder wick, and I also use a desoldering iron every once in a while. To start the design process of creating a custom PCB, we start out here in Kicad by creating a schematic. After we placed all of the parts, we assign footprints to all of them. For some of the parts, I had to create custom footprints so they can be compatible with our process, mostly because we have to use specific hole sizes because of the rivets that we're using. When we are done with the schematic and we assigned all of the footprints, we can close the schematic and we can open the PCB editor to create a layout. I already did this in advance before recording this video. Here we need to make sure that we use the correct track width. I used 0.44 mm and the vias are also the correct size. In this tutorial, I will not specifically show you how to create a schematic and a layout in Kicad. Instead, I will assume that you already know how to do this. If you don't, I have a link in the video description that can help you get started in Kicad. One of the important design guidelines when creating a homemade PCB is that you have to keep a little bit of a distance with other nets around the vias that you're placing. I recommend keeping 0.8 millimeters clear around every via. Now you might be wondering why I used exactly 0.44 millimeter wide tracks. This has to do with the track width compensation that we now have to do. Here you can see a list of track widths that I recommend you to use depending on the pitch of the parts that you're using. Any track size that is bigger than 0.54 mm can also be used. Going lower than 0.34 mm has not been tested yet. For vias, I use 1.6 mm diameter and 0.8 mm hole diameter. That is dependent on the rivets that you're using. Why do we need to do track width compensation, you might ask? The reason for this is the anisotropy of the laser focal spot. This picture here shows how that turns vertical tracks thinner and horizontal tracks thicker. We need to compensate for that within Kicad. We can calculate the degree of our focal spot anisotropy with this formula right here. For the IKEA K1 Pro that I'm using with a focal spot size of 80 micrometer by 60 micrometer, the degree of focal spot anisotropy is 0.143. Now let's perform a track width compensation for our Kicad board layout. I will place a 0.5 mm pitch component into our board layout and I will connect some vertical and some horizontal traces to it. I use the thickness of 0.34 mm for those tracks. Now let's run the Python script that will do the track width compensation for me. I will go to the Kicad scripting console and I will run this command right here. This Python script that was just executed changed the track widths of the vertical and the horizontal lines. It made the horizontal lines thinner and the vertical tracks thicker. It also did this over here on our actual board layout. Now that is already looking pretty good, but there is one issue here at the component with a pitch of 0.5 mm, and as you can see, the tracks don't fully extend to the pads. And what I'm going to do is I will manually make them longer. This way we can actually solder components onto those tracks, because obviously those pads right here are way too thin for solder to connect to them. Before I move on with the rest of the tutorial, I just want to quickly show you this Python script that I just executed. In this Python script you can change some of the settings and you have to adapt the degree of anisotropy to your specific laser model. In my case, I choose 0.21 for it after some experimental testing. I showed you how to calculate the degree of anisotropy earlier in the video. Most of the time, the manufacturer of your laser engraver will give you all of the required information. I've put a link to the GitHub repository where you find this Python script in the video description. Now let's create a folder on our PC for the production files. Now over here in the board layout, I will go ahead and I will remove this part again from the layout because obviously it's not part of the design and it was just for demonstration purposes. Before I'll finish up this board design, I just want to quickly talk about the vias in both of those corners right here. Those vias do not serve a technical purpose. They do not create any connections on the board. Instead, those are synchronization vias. They will become important later and they will make our life easier during production. Now that we are done with the board design, it's time to export the production files. You have to go to plot right here, select the plot format DXF. The included layers gotta be front copper, back copper, and edge cuts. Drill marks needs to be set to actual size and the export units gotta be millimeters. We then select the folder that we want to export to. in this case, the folder that I just created. We're going to select it. It's going to ask me if I want to use a relative path to Kicad. I'm going to select no, and then I'll hit plot. We're now done in Kicad. Before I will move on in Lightburn and we will create the production files for the laser, I just want to quickly explain to you why those footprints for parts with a smaller pitch look the way they do. Essentially, what I did here is I took a footprint that was built into Kicad and I made the pads smaller. The reason for why I did this is because if we do a drag width compensation, the way I just showed you, the pad size in the vertical and the horizontal direction is dependent on the orientation of the part. So there's no reason to actually have the pad size predetermined by the footprint. Instead, the pad size will later get determined by the drag width compensation. It's now time to import the DXF files that we exported from Kicad into Lightburn. When importing the edge cuts layer, we remove the drill marks. Because this is the outline of a copper fill zone, I move it to layer 1. Layer 1 needs to be in line mode and layer 0 needs to be in fill mode. We can look at a preview of our program right here. It's going to tell me that there are 42 shapes that are duplicates. I will press show me and then delete. Now I can press preview again and it will show me a preview of our laser program. You can use the preview window to double check if your settings are correctly. Everywhere where it's black here, it's going to cut, therefore the paint will be removed and therefore the copper will be removed. Where it's this red color here, no copper will be removed, and those are our tracks in the end. One thing that you always have to do is you have to mirror one of the layers. I choose the back layer for this. Press mirror selection right here. We also move them closer together. Now let's adjust the settings on both the layers that we're using. For the fill layers, I usually like to go with a speed around 2000 millimeter per minute. I'm going to choose 2400 here. I also like to set the power to 22%. I also select cross hatch here and I increase the overscanning a little bit, and I also set the line interval to 0.08 millimeters. The settings of the line layer are not that important. I like to go with a speed of 1500 here and also a power of 22%. Everything else can be left the way it is. Now there is one more step that I want to quickly do. I can go to layer 2 here and I can just quickly draw a little rectangle right here around our entire program. And it's going to show me right here the width and the height of this rectangle. I'm going to note down those numbers. After that, I can remove the rectangle again. Now we can move on with the next steps. Before you continue, you might want to check the preview window again. Make sure to also save your file. If you haven't already done it, take your spray paint and paint your copper board with black paint. Make sure to move the can thoroughly and shake it before using it. The paint needs to be water resistant, a matte finish is recommended. You don't have to use primer, also don't grind the surface of the copper, just make sure it's clean before painting it. Do not touch the copper board with your bare hands because that will leave greasy fingerprints on it. When I finished the production files in Lightburn, I measured the size of the PCB using a rectangle at the end. Cut out a rectangle which is slightly bigger than that. I marked it with a pen. Using tin snips is easy when the board is only 0.8 mm thick. I don't recommend using a saw or an angle grinder for cutting. This will create a lot of unhealthy dust. Tin snips are by far the best method of cutting PCBs. Of course, the paint should have dried before cutting the board. Next up, I glued some double-sided tape in all four corners of the board to stick it to the honeycomb work plate of the laser. Before starting the laser, I recommend already filling the etchant into the etching setup. Use a funnel for that. Turn on the heater and the air pump. It will take a while to heat up. The temperature needs to be around 45 degrees Celsius. If you start out, you will first have to mix the sodium persulfate powder with water. Use distilled water for that and follow the manufacturer's mixing ratio recommendation. The etchant can be reused a lot of times. This etchant that I'm using has been in use for more than 3 months now with no signs of deterioration showing. Every once in a while I have to refill a little bit of water into the tank. The etchant can be stored in a simple container. I use a fuel container for that. I poked a little hole in the top of this container to avoid pressure buildup. Be very careful when handling the etchant. If it comes into contact with certain surfaces, especially clothes, it will damage them irreparably, like it did with this carpet right here. You don't want to ruin your best clothes this way. Now turn on the laser engraver and connect it via USB. Make sure to not disconnect it while the laser is running, since the laser is controlled via USB streaming. Your PC needs to stay connected and turned on. Stick the PCB into the laser engraver's working area next. Make sure it sits straight and it is even. Sometimes cutting the board can bend it a little bit. Next, use this button to frame the laser. You can move the production files around by selecting them with your mouse and dragging them around. When the laser is framing, it will move around the perimeter where it will engrave. Move the production files around and hit frame repeatedly until the framing perimeter is perfectly within the board. Next, I used the 8 mm focus block to correctly adjust the focus of the laser. Your laser model might also be able to do this automatically like mine, but I don't use this feature at the moment. With the laser properly focused, do one last check by framing the laser. The laser is now ready to go. Hit the start button to start it. This PCB took roughly half an hour to engrave. I recommend setting up a webcam near the laser so you don't have to be in the same room to monitor it. Always keep an eye on your laser while it's running. Make sure to get proper ventilation in the room when the laser is running. I connect this air tube with a fan to the outside and I keep the window open. Make sure nobody can access your laser unintentionally. This step is the most safety critical of all. Make sure nobody gets hurt and nothing gets damaged by adhering to all relevant safety guidelines. The laser is now done. This is how the board now looks. Pretty good so far. You can turn the laser off again and disconnect your PC. Now look how dirty this board is when I rub my finger across it. We need to remove this dust with water to make sure it doesn't contaminate the etchant. Pour water over that board and rub your fingers across it until it is clean. Also remove the double-sided tape before putting the PCB into the etching container. After the dust has been removed, I insert the PCB into the etching container. I let it sit in there for 10 to 20 minutes and I check the state of it regularly. Before putting the PCB into the container, I make sure the temperature is at least 40 degrees. It is important to keep in mind that creating bubbles in the etching container will cool the liquid down again. So if the temperature is at 45 degrees without bubbles, turning them on will cool the liquid down again. The temperature needs to be 45 degrees with air bubbles on. When the PCB is ready to be taken out of the container, you can shine a light source through it like this. Make sure all of the copper is gone and there are no shorted nets left. After you take out the PCB, make sure to dry it immediately to stop the etching process. We now don't need the paint on the board anymore. I will remove it with acetone. Make sure to do this in a well-ventilated area. I recommend outside. By rubbing some tissues over the board after applying the acetone, I can just rinse the paint off. After removing the paint, you can use a multimeter to check that all nets are isolated from each other as intended. Now I cut along the board outline with the tin snips again. Now I drill in the synchronization vias that I showed in Kicad. I do that on both sides of the PCB separately. Make sure to do this as accurately as possible. This is integral for the proper alignment of both sides. If you didn't place synchronization vias, you will need to drill two identical holes on each side of the PCB. For that you can use some other via or a bladed through hole of a component. Using synchronization vias in two opposing corners of the PCB is highly encouraged. Now you need to align both sides of the PCB. Insert a rivet into both synchronization via holes. If you did the last step precisely, the holes on both sides should exactly match. If not, you did not drill them accurately enough or you forgot to mirror one layer in Lightburn. I use a rivet brass tool for this step. Now both sides are connected and they are perfectly synchronized. We can now drill the rest of the holes. I drill the holes at around 25,000 RPM. The drill bit has a diameter 0.1 mm larger than the rivet's outer diameter, as the rivet manufacturer recommends. Using a vacuum cleaner to suck up the PCB dust helps with visibility while drilling. I use a drill press attachment for my rotary tool to do the drilling. Using a normal cordless drill for this is not going to work. The drill bits are very easy to break. Normal cordless drills don't reach a high enough RPM, and if you hold them just a little bit sideways, the drill bit will break. Now it's time to use the rivet press tool to put the rest of the rivets into the board. After placing the rivets, you can use the multimeter again to check for unintended short circuits or missing connections on the board. You don't need to put rivets into every hole, only in the ones that have connections on the non-solder side of the board. Now the PCB is finished and I can start soldering parts to it. Now I finished soldering. Keep in mind that you should do the soldering step very soon after the board is finished. The copper will start to oxidize now, which will make soldering difficult after a couple of days. When the copper of the board oxidizes after soldering, it is okay as long as you don't need a spot on the board as an electrical contact. The oxidization will not affect conductivity of the traces. If you need a good electrical contact on the surface of the board, you can do chemical tinning or put solder tin onto the relevant spots. For soldering the parts onto the board, you don't need to follow special rules. You can do the soldering like with any other PCB. You should keep your Kicad file open on your computer for reference. There is no silk screen on the board, so you will need to check in the board layout file what component needs to be placed where. After soldering is done, you can check if your PCB works as intended, which I will do in the next couple of days for this board. Now we are at the end of this video. I hope you found this helpful. In the video description there is a GitHub repo with the Kicad board layouts, Lightburn files, the Python automation script for Kicad and a step-by-step instruction list. I will keep this repo updated if I make changes to the process in the future. Before you attempt this process yourself, check the repo and my YouTube channel for the most up-to-date information. To get started with this process, a big initial investment is necessary, but the recurring cost for PCB material and etchant is extremely small, so it will amortize quickly if you use this method regularly. Besides PCB etching, a laser can be used for many other purposes too, like cutting and engraving wood, like my channel logo that you can see right here. If you need help with building your DIY PCB manufacturing setup, you can always reach out to me for help. That's gonna be it for this video. Thanks for watching. Bye bye.